The first question asks, how many osmoles per mole are provided by ferric chloride? So the ferric ion has a charge of +3. Chloride has a charge of -1. We get the subscripts by crisscrossing. So iron, there'll be 1 of those. Chloride, there'll be 3 of those. And the osmoles per mole we will get by just adding up the total number of ions in the salt. So 4 osmoles per mole. Next question, what is the percentage strength of a 1 osmole per liter solution of sodium bicarbonate? So percent strength is going to be grams per milliliter times 100. And we're starting out with 1 osmole per liter of a solution of sodium +1 bicarbonate -1. Okay, so the liters need to be converted to milliliters, and osmoles need to be converted to grams in order to solve this problem. We know that 1 liter is 1,000 milliliters, so we've kind of got that under control. Just need to convert osmoles to grams. And then to do that, we'll need 2 conversion factors. We'll need the osmoles per mole of sodium bicarbonate, and then we'll need grams per mole. So we can go osmoles, moles, moles, grams. So that will involve getting the subscripts. So we've got everything there. And we can tell, I think the easier one is to add together the subscripts to get 2 osmoles per mole. So that's one conversion factor. And then the other thing would be molecular weight. So we have 1 sodium with a molecular weight of 23, and we have 1 bicarbonate that has a molecular weight of 61. And so the molecular weight of the whole salt is 84 grams per mole. All right, those should be the 2 conversion factors we need. We can start doing proportions now. We have 1 osmole. We want to know how many moles that represents. And we know that for this salt there are 2 osmoles per mole. And so that means that in 1 osmole we have 0.5 moles. Okay, and then the next step was to take the 0.5 moles and see how many grams that is. So 0.5 moles is x grams to 84 grams per mole. And so x here is 42 grams. All right, so we have number of grams, we have number of milliliters, and so we just have to calculate the percentage now. So 42 grams over 1,000 milliliters times 100. We divide that through, and we get 4.2%. 4.2% is the percentage strength of the 1 osmole per liter solution of sodium bicarbonate. Okay, the last one on this page is that we have a solution of sodium chloride at a concentration of 80 milliosmoles per liter, and we want to know the solution's strength in milliequivalents per liter. So we're going from 80 milliosmoles per liter to how many milliequivalents per liter? So the liters are fine, we've got that taken care of. We just need to convert milliosmoles to milliequivalents. And so for that we'll need 2 conversion factors for sodium chloride. So crisscross. We're going to need osmoles per mole to get to moles, and we're going to need equivalents per mole to get back to equivalents. So osmoles per mole are the two subscripts added together. That's 2 osmoles per mole. And equivalence is one of the subscripts times the superscript. So 1 times 1, and that is 1. 1 equivalent per mole. And those are the 2 conversion factors we'll need. So we can start out with 80 milliosmoles. How many millimoles is that? If there are 2 milliosmoles per millimole, and hopefully you're comfortable with using the same value if we change the top and the bottom in the same way. So X there is going to be 40. And then we want to know how many milliequivalents for 40 millimoles. Given that, there's 1 milliequivalent per millimole. Well, that number stays the same. So we've got 40 milliequivalents, and it's still in 1 liter. So 40 milliequivalents per liter is our answer. In the final problem, we have an IV bag that has several components in it. It has D5NS, and it has potassium chloride that's been added to it as well. So we have several things to think about. We've got 5% dextrose, and we've got the normal saline, that's 0.9% sodium chloride. And we also have the potassium chloride injected to a concentration of 25 milliequivalents per liter. So the goal here is to be able to take each of these components and convert them into milliosmoles per liter, and then sum up the concentration in milliosmoles per liter for the entire solution. So starting with dextrose, we have 5 grams dextrose per 100 mils of solution. We're going to need to be able to change 100 milliliters into liters, and so we can get that out of the way. How many liters are 100 milliliters? If 1 liter is 1,000 milliliters, so X is going to be 0.1 liter. And so we can use that later for the 100 mil volumes that we encounter. And now we can just worry about the 5 grams and getting it into milliosmoles. So the first place we go is to moles. How many moles is 5 grams? For that we need to know the molecular weight of dextrose. And that's given on the table. Dextrose is actually the same as D-glucose. And so the molecular weight of dextrose, or D-glucose, is 180 grams per mole. And so X for that is going to be a pretty small number. We'll try to include quite a few decimal places while we're in the calculation stage of this. So 0.0278 of a mole. All right, next step then is to go from moles to osmoles. So how many osmoles are 0.0278 moles if dextrose has how many osmoles per mole? Well, dextrose is a covalent compound, so when you dissolve it in solution, it doesn't break up into ions like a salt would. That means for every mole you dissolve, you get 1 mole of particles. And so this value is just going to stay the same. We have 0.0278 osmoles of dextrose. All right, and then the last thing is, if we have 0.0278 osmoles, how many milliosmoles is that? If one osmole is 1,000 milliosmoles. So X here is 27.8 milliosmoles. Okay, so that means that for dextrose, 5 grams per 100 milliliters is the same as 27.8 milliosmoles per, we calculated the volume here, 0.1 liters, which is 278 milliosmoles per liter. Okay, so that's our answer for the 5% dextrose, and we need to do this for each of the components of the IV solution. So let's do the same thing for sodium chloride. 0.9 grams per 100 mils of solution. 0.9 grams is how many moles? And the molecular weight of sodium chloride is 23 plus 35.5 from our chart. It's 58.5 grams per mole. So X here is going to equal 0.0154 moles. Okay. And then next we need to know how many osmoles is that? 0.154. And what's the osmoles per mole of sodium chloride? Well, there's one of each of these ions, so we add them together to get osmoles per mole. That's 2 osmoles per mole. So X will equal 0.0308 osmoles. Okay. And then 0.0308 osmoles is how many milliosmoles? And there's a 1:1000 relationship between milli and the base unit. So that gives us 30.8 milliosmoles. Okay, so now we just recognize that 0.9 grams over 100 mils is the same as 30.8 milliosmoles for the grams and 0.1 liters for the 100 mils, and that is 308 milliosmoles per liter for the sodium chloride. Alright, so we've got dextrose and sodium chloride covered. Last one is we have 25 milliequivalents per liter of potassium chloride. And so we need to convert the milliequivalents to milliosmoles, and liters is already covered. 25 milliequivalents. We always go to moles first. So how many millimoles is that? And so we need to know the equivalents per mole, which is the same as the milliequivalents per millimole for this salt. And we can pick either one of these. You multiply the subscript times the superscript, and it's just 1. So milliequivalent stays the same as millimoles. 25 millimoles. Okay, and then we want to know how many milliosmoles are represented by 25 millimoles given an osmole per mole for the salt of, we add the subscripts together, 2 milliosmoles per millimole. That means X is going to equal 50 milliosmoles. All right, so 25 milliequivalents per liter is the same as 50 milliosmoles per liter. All right, now we have the milliosmoles per liter for all three of these, and we can just add them together. Let's just do this in the corner here. 278 plus 308 plus 50. Add all those together, we should end up with 636 milliosmoles per liter.